So in the last video, we were talking about how we wanted to calculate the slope at a specific point, x, and we decided that to calculate the slope, we needed 2 points, and we figured out that it would be really hard to find a point, a second point, on this tangent line, and the tangent line basically approximates the slope, right? If we know the slope of the tangent line, that's the same slope of where at this particular point, because we don't know any numbers on the tangent line. Like even if we had the function here, the tangent line is some random line off of the function that we are not going to be able to get numbers for. So we got our second point on the actual curve because we could find, the values of that point. But we said that this slope of the secant line would be horribly wrong. Nevertheless, at this point, this is the best idea we have. So I'm going to actually show you how to calculate the slope of the secant line, knowing that it's wrong, knowing that it's a really bad approximation of the tangent line, but knowing that so far that's the best we have. Okay, so how do I calculate slope? Rise over run, y2 minus y1 over x2 minus x1. So what's y2, right? Think of this as x, so let's just go over here. So we have, this is x plus h, f of x plus h, and this is x comma f of x. Okay, so y2 is f of x plus h. So f of x plus h minus y1. y1 is f of x. Okay, over x2, which is x plus h, minus x1, which is x. Okay, so cleaning this up a little bit, the slope of the secant line, which is otherwise known as the difference quotient, is f of x plus h minus f of x. That's the change in y. And you guys see how the x's here would cancel, right? So then I would just have h. So the change in y over the change in x, the slope of the secant line. And that's a really bad approximation. It is not equal to the slope of the tangent line, and this is, really a big error, okay? So let's try to fix it, because I don't like to have big errors in math. We want to try to be as precise as possible. Okay, so one of the things we can do is say, why did we have to draw the secant line in such a bad way? Like, could we have done a better job of this? This second point is really, really far away from the first point. So what we can do is start making better secant lines, right? So what if I drew a second secant line that was like a little bit better? Like I'll try to draw this here, right? Where the second point was a little closer to the first point. And do you guys see how the h, or the distance between those x values, is a little smaller? So h is getting smaller. And do we see how the second secant line that I've drawn in green is a lot better than the first one I drew in purple? And if you understand that logic, you might be saying, well, can't we do even better? Like, can't you draw an even better secant line? Can't you get even closer? I think I can, right? So this drawing is going to get a little crowded, but I think I can get a little closer. So what if I do this? That's even better, right? Look at that. Look at the h. Look at that distance. It's getting smaller. H is getting even smaller. And if I keep continuing with this logic, what I can do is I can take what is called the limit, and I can let h approach 0. It's not going to equal 0, this distance here, but I can let it get really, 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 really infinitely close to 0, arbitrarily close to 0. So close to 0, in fact, that I almost can't tell the difference. So what I can do is take my bad secant line that I started with and keep drawing better and better approximations of the secant line. And as I do that, what's going to happen is the h, the distance, is going to go to 0, and the secant line is essentially going to approach or come super, super close to the tangent line. So close, in fact, that you won't even be able to tell the difference. And the slope of this secant line, right, is going to be so close that it's going to almost equal the slope of the tangent line, but for this infinitely small difference. So the idea is essentially in calculus, right? So you're going to basically keep this formula, okay? But we're going to take the limit as h approaches 0, okay? And that is going to be the slope of the tangent line, which is known as, can we see this okay? The slope of the tangent line, that is known as the derivative or the rate of change, okay? So the idea is, if I can get the secant line to approach the tangent line and that h gets really, really, really close to 0, the secant line and the tangent line will be virtually the same and my slope will be pretty accurate. Just a quick note on notation. The derivative, you'll see this notation, it sort of looks like f prime of x. That indicates derivative or rate of change. So we creatively used 2 points, which we needed, and we made a better approximation. As h approaches 0 and the secant line approaches the tangent line, the error between the slope of the secant line and the tangent line becomes so small that we're comfortable that whatever that derivative or slope is, it's pretty accurate, right? The points are so close together, they basically touch, but we technically have 2 points.